Hello. This video is going to be a little bit different, and you might need to watch all of it if you really want to learn how to do these things on your own. How to measure the elevation angle and azimuth of a star at any time of the day. For a start here, I will not think about the Earth, I'll just think about myself as the observer, and the stars around me are painted on the inner side of this celestial sphere or celestial dome. The equator is the same level as you, and whatever above it is above your eye level, and whatever below it is below your eye level. And this line here from North Pole to South Pole is from your head to your feet. And why your head and your feet is oriented in that way or in that manner, because this is the rotational axis that you are spinning in. For simplicity, I'll presume that you are stationary, and this celestial sphere or celestial dome is spinning around you. And so any star in that celestial sphere, if you are spinning counterclockwise, the star will be spinning clockwise this way. And you're here in the middle. The line of sight from your location to that star along 24 hours will form a cone like this. You're here, still no Earth, just you and the star. If the star is higher than you or have a declination angle, this is the declination angle measured from the equator to the star. Not the equator of the Earth, the equator of the celestial sphere. I think they call it, I don't know what they call it. But anyway, this is a positive declination angle, and if the star is below the equator, then it's a negative declination angle. Now I made something here. This is the Earth, of course not to scale, and this is our cone here. This line here, this red line, is parallel to the rotational axis of the Earth, and the star is not here, the star is far away, but it's the same thing. I'm just scaling down the cone. So if the star has a high declination angle, then you'll be seeing it most of the day, and if it has less declination angle, you will see it less time until it's on the equator or the celestial equator. If you look top view like this is 180 degrees, and if you translate it to time, that will be 12 hours. And that's the case of the sun during the equinox. So let's have a negative declination angle. Let's look from top view, and you see now that the angle of the star from starting from rise until setting is less than 180 degrees. That means less than 12 hours. So let's take it more down. Let's look top view, and you can see that the angle is getting way less than the first one. And let's take it more down. I think I screwed something up here. This has to be a little bit up. Yeah. Look from top view. Right. Now, if the declination angle is more or less than this, then you are not going to see the star. The star is you should be moving south in order to see that star. Now let's give an angle that is almost 23 degrees. Yeah, this is around 23, this angle here. And I think this would be like latitude of 45. So this would be the angle from here around this arc to here is like what? Almost 270 degrees. Translating that into hours, that would be around 18 hours. Okay, now let's move towards the North Pole. And we have to make sure that the tip of the cone is exactly on the Earth. So I'll take the cone and this rotation axis and put it up here. Now see, with the same declination angle, you can see the sun all day beyond a certain latitude. So this is the idea. Now, how to calculate the elevation angle and the azimuth of that star on a specific time, and I will start from from the star rise. Okay, so take it down a little bit, decrease the declination angle. Yeah. Okay, so we will take this into a drawing that we can analyze and get some angles from. So the first thing I'm going to do is to draw the surface of the Earth. This angle now is like 45, so that means that's 45 latitude. This angle is here on the North Pole or the South Pole. So we'll make it like this. That's almost 45. And let's get back to the 3D. Looking at this drawing here, let me fix the cone. Okay. So this is the star is below the horizon for a certain time, and then it rises, and then here it's at the 90 degrees position, and here it's at the 180 degrees position. Looking from top view, if this is the 0, this is the 90, 180, 27. So we'll try to take this and this and this line into our drawing. So we'll give the star a red color. So the star passes from the 0 to the 90 and then to 180. And where are you in this place? We'll put you here. Just give you some color. So this is where you are. So at the moment the star is rising, here, this moment, can we conclude the angle? Well, let's see. First we have, oh sorry, this Sorry, I'm kind of doing this live and I'm not going to do any editing, so I'll be pausing sometimes. This is my triangle here, and here this angle is 45. I think it looks more than 45. Let's call it 50. Okay. Now, remember this is the 0 and this is the 100. So this is my cone here, and I'll draw it in yellow, same as the one you saw. I don't think that they are the same, so, but never mind. Anyway, so this is our cone. Where's our 90 position? Our 90 position, I'll give it a color. This is 90 position of the star. The star at the star rise is here, and I'm here. That distance is, say, 100. Not this projection. I'm talking about the actual distance between me and the star is 100 all the time. It's always 100. This projection is not 100. What we see here, this black line, is a projection of the 100. And if we have that projection, we can tell the azimuth of the star when it's rising. So let's get this length. First of all, this blue line, we need it. This is the first thing that we're going to conclude. So first, let's see what we have in order to get the length of this blue line. This is our starting point. The first thing is we have this length, and we say just give it in numbers, say 100. Then we have this, the equatorial plane, or the level of yours. This would be the declination angle of the star, and this angle is equal to this angle, so this will be the declination angle of the star. And then we have the latitude line here. This is your latitude line. So we have a length here, and we have a right angle here, and we have the declination here. So the blue line would equal 100 multiply Come on, I'm recording here. Okay, I'm recording. So, sorry, it's my wife in the kitchen. So the blue line would be 100 multiply sine of the declination angle. Why isn't it right here? Sine the declination angle. So what next? Yeah, we want this one, the black line. The relation between the black line and the blue line, this is the hypotenuse. So this would be the blue line divide cosine the latitude. So equal the blue line, call it B. Then divide cosine the latitude. Now let's go to the spreadsheet and do these calculations, because I'm not going to do by hand or by calculator. So here's the parameters that I mentioned. The length is 100. Latitude is how much was the latitude? Now this angle was 50, so the latitude would be 40. And the declination was 30. So the blue line equals 100 sine the declination. So 100 multiply sine. I have to put radians because the Excel sheet doesn't understand degrees. Radians, the declination. That is it. And then the black line equals the blue line divide cosine the latitude. So this equals the blue line divide cosine radians the latitude. Alright, now we have our black line. Now I'll go in detail to explain the azimuth. If you are looking in that direction, top view on your location, that would be the north. And what you're going to see is this is the line of the north, and then this is the angle to the star. This here is the black line, the projection of the 100, and this is the 100, and so this will be the sun or the star rise angle. This will be the star rise angle, and the relation between this line and this angle is cosine, or the inverse cosine of dividing this by this. So let's go to the Excel, and the angle equals degrees of a cosine the black line divide 100 to get me this star rise angle. Black line divide the 100. I have to put degrees because the angles on Excel don't show in degrees, they show in radians. So yeah, this is the star rise angle. Now let's go to a real life example just to confirm how we're doing. And to be honest, during this video I made a lot of mistakes. I had to cut and edit, or just pause and re-record again. So I have here the latitude is 30 and the date is 21st of June. That's summer solstice. So the declination angle of the sun is 23.44, and this is the latitude. So let's put these angles in the Excel. The latitude is 30, the declination is 23.44. Now you see the star rise angle, or the sun in this case, is 62.6, and here it is almost 62. So there's like 0.7 or 0.8 degrees of a difference, but I'll explain this later why this error is here. But notice also when you do this on suncalc.org, this is the sunrise here. When you click the sunrise, this is the information. The altitude is minus 40, so this is not the physical sun because of refraction. So if we add a couple of minutes, so when the altitude of the star or the sun is 0.08, the angle is 62.35 and 62. Yeah, okay, so that's very close. But again, there's still things that I'll be explaining in the next episodes. I cannot explain it right now. There's a series of stuff that I have to explain first. But yeah, there you go. Just 4 equations to conclude the sunrise or the star rise angle at any time. and the next episode will be the elevation angle of the star. So see you there.